Okay, it looks like we've got everybody here. Today we're going to go over Chapter 1, Section 2, and that deals with sets. So you can think of a set as a collection of elements. So, for example, if C is the set of all countries that are currently in the United Nations, then the United States is an element of C. And likewise, if I is the set of all integers from 1 to 100, then the number 57 is an element of I. So a set is denoted by the capital letter S in this particular case, and membership in a set is denoted by the Greek letter epsilon. So X epsilon S means that X is an element of S. The axiom of extension says that a set is completely determined by what its elements are, not the order in which they may be listed, or the fact that some elements may be listed more than once. So take a few minutes and review these questions on using the set roster notation. And the set roster notation means we have a set that's small enough that we can denote it by just listing out its elements. Okay, so let's take a look at these. For part A, sets A, B, and C have exactly the same elements, 1, 2, and 3. So therefore, A, B, and C are simply different ways to represent the same set. For B, the set with an element of 0 is not the same as the number 0, because the set with the one element 0 in it is a set with one element, whereas 0 is a number. So those two are not equal. For part C, the set has two elements, number 1 and a set whose only element is the number 1. And for part D, U1 is going to be 1 comma minus 1. U sub 2 is going to be 2 comma minus 2. And U sub 0 is going to be 0 comma minus 0, which in turn is equal to 0 comma 0, which in turn is equal to the set of just 0. Okay, so some sets are used so frequently they have their own symbol assigned to them. The set of real numbers is designated by the capital R. The set of integers is designated by the capital Z, and the set of rational numbers is designated by Q, capital Q. So if we can think of the points, all the points on a line, that's what the real number system is, how it's usually pictured. So we have a number 0, which is the middle point or origin, and a unit of distance is marked off from the origin. Each point to the right of the origin corresponds to a positive real number found by computing its distance from the origin. Each point to the left of the origin corresponds to a negative real number, which again is denoted by computing its distance from the origin and putting a minus sign in front of the resulting number. So the set of real numbers has 3 parts: positive real numbers, negative real numbers, and the number 0. 0 is neither positive or negative. A real number line is called continuous because it's imagined to have no holes in it. The set of integers corresponds to a collection of points located at fixed intervals along the real number line. So every integer is a real number, and because all integers are separated from each other, the set of integers is called discrete. The name discrete mathematics comes from the distinction between continuous and discrete mathematical objects. Okay, so a question is, what does continuous and discrete mean? Well, you can think of continuous as how much. So we can have fractional parts. So we can go 1/3, and we can have that split in 2 to 1/6, and that split in 2 to 1/12 and 1/24, and so on. So we can keep getting smaller and smaller because we'll always have a point that we can get to. That's continuous. Discrete, you can think of as how many. Here we're counting individual whole things. So we have whole numbers to represent them. So another way of designating a set when we have a large number of elements in the set is the set builder notation. And here we give a rule that is going to filter out elements that don't belong in the set, or you can look conversely, it's going to be filtering in those elements that do belong into a set. So our denotation now is, as we see in the formula at the bottom of this rectangle, the curly braces means the set of all x that's an element of S such that x has this property P, or the property P is true for x. So let's take a minute and kind of review our understanding of what we've covered so far on set builder notation and answer these particular questions. Okay, started up the recording, resumed it. So the first one is the set of all real numbers. So as we saw, we can think of this as numbers on a line, or just a line between -2 and 5, and it includes all of the continuous set of numbers along that line. It does not include -2 and does not include 5. For B, that's the set of all integers between -2 and 5, not including -2 and 5. So that's going to be the set of, and we can use set roster notation here, -1, 0, 1, 2, 3, and 4. And finally, for part C, since all the integers in Z plus are positive, that's going to be the set of numbers 1, 2, 3, and 4. Okay, next let's talk about subsets. So if A and B are sets, then A is called a subset, and the notation for that is an extended C with a line underneath it. And A is a subset if and only if every element of A is also an element of B. So what it means logically is for all elements X, if X is an element of the set A, then X is an element of the set B, and that means that X is a subset of B. So it follows from the definition of a subset that for a set A not to be a subset of set B means there's at least one element of A that is not an element of B. And we denote that with our set membership symbol with a line through it. A proper subset is where you have A as a subset of B, and B has at least one element that is not in A. So in other words, they're not the same set. Okay, let's take a look at these questions, and we'll review them in just a moment. Pause this. Okay, so to recap, only answers A, D, and F are true. B is not true. For B to be true, the set with the numbers 1, 2, and 3 would have to contain the element which is subset or a set with the number of 2 in it. So the set with a number of 2 in it is not the same as the number 2. So again, the only elements of 1, 2, 3 are the numbers 1, 2, 3, and none of those, including 2, is equal to the set with the number 2 in it. So therefore, B is false. For C to be true, the number 2 would have to be a set, and every element in the set 2 would have to be an element of 1, 2, and 3. This is not the case, so C is false. So 2 is a number, and it's not a set, so it can't be a subset. And then finally, E, which is false. For E to be true, every element containing only the number 2 would have to be an element of the set whose elements are the subsets 1 and 2. But 2 is not equal to either the subset with a number 1 in it or the set with the number 2 in it. So E is false. In other words, the element of subset of set with the number 2 in it is 2. That's the element in that subset on the or that set on the left. And the elements of the set on the right are actually sets, not numbers. Okay, let's look at the Cartesian products. Now we mentioned that a set doesn't matter what the orders of the order of elements are in a set. It just matters what elements you have. We have another concept known as an ordered pair, and in an ordered pair, the order of the elements does matter. So for the ordered pair A comma B equal the ordered pair C comma D means that the respective elements would have to be equal as well. Let's take a look at these ordered pairs. Take a minute to think of those. Okay, I'll resume. So is 1 comma 2 the ordered pair equal to the ordered pair 2 comma 1? No, by definition of equality of ordered pairs, the ordered pair 1 comma 2 would equal the ordered pair of 2 comma 1 if and only if 1 equals 2 and 2 equals 1, and that is not the case. For part B, yes, by definition of equality, the ordered pairs are equal only if 3 equals the square root of 9 and 5/10 equals 1/2. Both those are true, so the ordered pairs are equal. Yes, that's correct. So we have to assume that we're looking at the set of positive integers for the square root of 9. So 3 rather than the other. So yeah, 3, we're assuming that it's going to be the square root of 9 would be the 3. And then for part C, in the ordered pair 1, 1, the first and second elements are both 1. Okay, a Cartesian product is where you take each element of the first set, and it's denoted by A, X, B, and it's called A, and it reads rather A cross B. So we take each individual element of A and pair it with each individual element of B, and then we go to the next element of A and pair it to each element in B, and so on. So it's the set of ordered pairs A, B, such that A is an element of the set A and B is an element of the set B. Let's take a look at some of these. Okay, resuming. A cross B in the in this example is going to be 1 paired with U, 2 paired with U, 3 paired with U. So we have the ordered pairs 1 comma U, an ordered pair 2 comma U, an ordered pair 3 comma U. And then we have the ordered pairs where we go to the next letter in B, 1 comma V, 2 comma V, 3 comma V. For C, we've got the ordered pairs of B times B. Well, B times B has 4 elements, the number of elements of B times the number of elements of B. So we're going to have U paired with U. So we're going to have a set of ordered pairs. The first ordered pair is U comma U. The second is U comma V. The third is V comma U. And the last is V comma V. For A cross B and B cross A, they each have 6 elements, which is the number of elements in A times the number of elements in B. Okay, let's do B cross A. B cross A, we're going to take the first element of B and pair that with the elements of A. So we're going to have the set of ordered pairs U1, next ordered pair U comma 2, next ordered pair U comma 3. Then we take the next element of B, which is V as in Victor, and pair that with each element in A. So we add to the set the ordered pairs V comma 1, V comma 2, and V comma 3. Okay, so we'll do B, how many elements? A cross B has 6 elements. This is the number of elements of A times the number of elements of B. B cross A has 6 elements. The number of elements in B times the number of elements in A. And B cross B has 4 elements. The number of elements in B times the number of elements in B. And then R cross R is the Cartesian coordinate system, basically. It's all the ordered pairs X and Y, where both X and Y are real numbers. And you've seen the horizontal and vertical axes that are drawn on a plane. That's R cross R, a Cartesian coordinate system. Okay, we'll reconvene next Tuesday.